and running as fast as possible. So today we have Sam from Nerve Solutions Group, and we've got Nick and Athon from Kelsen. They will be talking about how AI can basically disrupt the legal system. That's it for me. I wanted to keep it short for them to give you a better introduction.
Thank you, Ricardo. Good evening, everyone. I'm Sam Soliman from Nerve Solutions Group, and as Ricardo said, I'm joined by our partners from Kelsen, Nick and Athon, and we look forward to talking to you about AI in the legal industry tonight. So just a brief overview of what we're going to cover off. We're going to talk about our journey into AI, a bit about the first opportunity that we ventured into and some of the challenges that we face along the way. We're then going to go into a bit about the solution, the architecture behind that, and a deep dive into some of the models that were utilized. And then we're going to talk about some of the outcomes that we've been able to obtain from the model so far, and then a bit about the future opportunities and how we're preparing for that. So just briefly, Nerve Solutions Group is a business and technology solutions consultancy with a passion for digital transformation. We were formed last year as the 8th subsidiary of the Nerve group of companies, and we were established because we saw that there was a gap in quality digital transformation agencies for the legal SME market, and also that there was a lack of adoption of emerging technologies and changes to the legal business model. And we're based out of Brisbane. We've got about 40 specialist resources, from national practice lawyers to statisticians to mathematicians, and all the way down to help desk operators. So we're quite a diverse group of people. And for us, we started our journey about 9 months ago now, and I think probably a similar situation to what other people face is, AI, unlike other areas, like other business systems areas, like for instance, CRMs. If you want a CRM, there's Salesforce, there's Microsoft Dynamics, and there's Oracle, or maybe not Oracle, but there's big players in the market, an established market. But with AI, it's different. AI is still very fragmented. It's still very young, and the complexity, I guess, behind a lot of AI can be a bit daunting. And so, understanding where to start, I think, is a big issue, and one that we wanted to overcome. So we felt the best way to do that was to start, pounding the pavement. And we started attending groups like this. So I've been coming to AI meetups for quite a few months now. We started to ingratiate ourselves into the Brisbane network, and just to understand what was out there and kind of sort the kind of fact from fiction. And after meeting with several different consultancies, and we even met with some of the larger players who just send salesmen to talk to you, and it's quite clear they have no idea what AI is, but it just does everything. We come across some of the local Brisbane players, and that's where we found Kelsen, and since then we've formed a partnership, and we've been going through our first model. But I'll hand over now for Nick to give an overview of Kelsen.
Thank you, Sam, and it's good to be back at Brisbane.AI. I mean, we are becoming a little bit of a familiar face around here, but it's amazing to see so many people turning out at this event, 18 months after it really kicked off. So it's awesome, and thanks for coming along tonight to hear us babble on once again. It's quite amazing, actually, us partnering with Sam. I've got a law degree, and there's a few sort of lawyers or people with legal backgrounds in our office. So when Sam came along, we were really interested about how we can take what we'd been doing and what we'd been researching into a domain that some of us had very good knowledge of, but a domain that really is ripe for opportunity. And particularly for us at Kelsen, we have quite an interest in natural language processing, and for the legal sphere, that's quite important. It's a lot of documents, a lot of language. And so for us, it was a really interesting problem. Sam's been amazing to work with. The whole team at Nerve have been incredible to work with. And they brought us a really, really exciting problem that we're going to go through tonight. I have dragged along Athon, one of our ML engineers, and a dead set genius. And he's going to go a little bit deep on some of the models that we made, so hopefully we don't lose too many. But Max Kelsen's a little over 3 years old now. We're 25 people based in Fortitude Valley. We're focused on implementing artificial intelligence for real use cases, whether that's in the enterprise space, government space, or startup sector. We're interested in finding problems and taking them the whole way through to production. We also have a product that we've built called Cognitive CX, small plug, which is based on a lot of the NLP that we're going to talk about tonight. So that's basically us.
Thanks, Nick. Okay, so being an organisation with a number of different legal firms, we saw that we had a huge amount of historical case data, and along with the proliferation of AI tools and the increased accuracy of these tools and the increasing price performance of these tools in cloud computing, we saw that we had a real opportunity to leverage our history and enable better decision making. And so we took a specific litigation practice area where we had high volume and low complexity, so that it was kind of contained, but it also enabled us to be able to scale once the model was proven. We looked for pertinent indicators that would help us determine the case outcome, and that would then aid us in enabling us to make better decisions around the case selection and around the timing of the resolution and around being able to match cases then to lawyers. So understanding these indicators was critical for us in enabling or attempting to enable earlier resolution, because the earlier obviously you can resolve a case, then the less effort's involved in the case and less cost to the client. And that, you can imagine, would improve the experience for the customer to no end, and also helps being able to manage expectations of clients' expectations of the case as well, and as early on as we can possibly make that. So we were able to source about 10 years worth of case data, and with that we were able to derive about 200 plus features of where we felt that these features had a strong link to the outcomes that we were trying to achieve. And so this all looked great. However, then we come across one of our first problems, and it turns out that lawyers are not that disciplined when it comes to data entry. And so we had all this data, but the problem was we had sparsity in this data. So we had all these, we had about over 15,000 cases and 200 plus features. But when we started going through the data, we found all these holes, I guess, in the data, where you'd have some features that were populated for some cases, and for other cases, it wasn't populated. And that obviously poses quite a problem, because you can't put features, the same features in a model where you've got missing, where some cases are populated and other cases have null values, because the model will try to derive a meaning from that, or depending on the model, it'll have other implications. And you've got imputation that you can do, but then that could introduce bias. So we were faced with a problem where we had a lot of good data, but then we had missing data that was going to impact the overall project. But while the lawyers might have been lacked some discipline in data entry, what they're great at is writing. And so we found all these legal documents where we had a huge amount of data. And so then we had to look at, how do we extract that data? How do we take this unstructured data in multiple documents and then take that and through natural language processing and classification, and then turn that into structured data that could then get fed into our model. And I'll now hand over to Nick and Athon, and they're going to talk through this in some more detail.
Thanks, Sam. You basically said everything I want to say, but I'll find something else to say. No, the problem, actually, I was fortunate enough last week to see the astronaut Chris Hadfield speak twice. And probably the key takeaway from my talk for him, when he was speaking, was that he has this idea that smart doesn't really matter until you put smart to work. I'm going to flip that, and I'm going to say smart's really easy until you try and put smart to work. And herein lies the problem with this use case. We identified a problem that traditionally was what you would call low complexity, high volume, exactly what we would look for. We started to work on it, we see how lawyers entered data, and all of a sudden it became quite a high complexity problem, which was really exciting for us. And we're fortunate enough to have an NLP team, I think some of them are up the back, at least Claire's there, who did a ton of work to build a system that could extract the information that we needed out of these documents. Now, we've done a lot of natural language processing on things like tweets that are all of 140 characters long, or maybe a Facebook post, which is 100. But these documents are legal documents. They are hundreds of paragraphs long in some cases. They are extremely complex, and they contain a lot of information. So how do you easily, or relatively easily, extract the information from such a dense document? We went to our normal tools and we used What's in Knowledge Studio, and we've talked about What's in Knowledge Studio here a lot, right? Because it allows us to build extremely high performant entity extraction, relation extraction models very, very quickly. So this work was done over about 6 weeks by a team of just 2, and they were able to extract the features that we needed from medical legal reports, from case plans, from all of these different documents at scale. So what I was going to do tonight is actually, and I don't know, I've broken your computer, that's good. I don't know how technical the crowd is, but just because we have spoken about this a lot, hopefully it's going to work. I have a video of actually how to do this. questions. It's actually a super cool example, right? Because what we essentially did is we were trying to work out a way to demo this to people to give them an idea of what we're trying to do. So we found 50 people's LinkedIn profiles that we knew, and in every LinkedIn profile someone says, I'm Nick Therkelsen and I work for Max Kelsen and I'm the CEO and I went to University of Queensland and studied law for some ungodly reason. And it's a relatively structured piece of information, but if we wanted to be able to analyse who's in that data set, who they work for, what their occupation is, and where they studied, we need to work out a way to extract that out of the free text at the top of LinkedIn. So we only took 50 examples. We trained it in all of an hour sitting in a hotel room in Austin, Texas. And we essentially trained it to extract the data of our other panelists when we're in the US. And this thing performed at 96% accuracy on only 50 training examples and trained in an hour. So I'm going to say that example was super easy to do. What we did here was not so easy. But it's the same building blocks, right? It's a really good tool to be able to get down the road further. And I think this is a story about AI at the moment. We've got a lot of options out there, from open source models, frameworks, to off-the-shelf tools like WKS, to pre-built APIs. And what you've got to do is choose your battles. You cannot build everything from the ground up. It's just not feasible. What you've got to identify is, in my problem, where is it that the current tech doesn't solve it? And where is it that I can leverage things that have been done before? So for us, WKS gave us a performant entity extraction model, which is what we needed to solve our data problem, so that we could actually spend a lot more time focusing on feature engineering and the prediction algorithms, which at that point weren't solved. I think the exciting thing about working with Sam is he let us go on this journey. It was very much an experimentation. We didn't know if it was going to work. We didn't know what the results were going to be like. We were trying to do something that wasn't necessarily yet done, and then we have a massive sledgehammer of a problem come in front of us. We worked through it, and I'm going to let Athon take over, and he's going to get into the models that actually did the prediction, which is the interesting bit.
All right, great. Hi guys. So, the deep dive. All right. So, we've got a team of 3 guys at the moment who have been pushing really hard on, I guess, the research element, and this was a challenging problem at the kind of, in terms of the, yeah, definitely the data, but I guess we had a lot more experience previously on building custom models around deep learning and natural language and image recognition and all that kind of stuff. And this kind of really shook us up, because it was, the challenge was in the data, and the challenge was in going back to basics, really, on data science techniques and machine learning strategies that have been around for quite a while, but there's a big difference between taking a model, taking data that's kind of prepared for the model, and often the models are pre-trained with huge corpuses of data. So, you know, starting from the ground up on the data and driving insights there was a challenge. So we wanted to, I thought I'd just kind of articulate a few of the steps along this process that we encountered that could be valuable to anyone working in this kind of stuff. So those were the models, the selection, the imputation, encoding, and of course learning. So as Sam said, we were faced with a large corpus of data, over 200 features, and more than 15,000 cases to work with, but quickly realized that there was greatly varying levels of quality in this information. And I guess also that's some of the features are not going to hold correlation. So the first thing was to consult with the fields in the experts in the fields, and kind of distill what we could. So this wasn't even the initial sparsity analysis. So this was after distilling out a fairly large portion of what we'd come across. So the way this graph breaks down is it looks like we had it down to about 11,000 at this point, and across the bottom we would have around 80 to 100 of the features that we found to hold the most correlation and the ones that could contribute most. And you can see here, everything above that line is basically not a number or none. And so this was a big challenge, evidently, because any means of imputation is going to introduce some form of bias. So we had to be quite intelligent about our strategies around this and kind of find the needle in the haystack, so to speak. So
I think just to jump in to help, it's important to note, which I think is underpinning what we're talking about, is that the models do not like missing data, right? The missing data is not interpreted by the model like it would be by the human, in that that data is just missing. The missing data is interpreted as being pertinent, and that's the problem with sparse data. A null or a zero is something that becomes part of the analysis, and so you can't just put in data with missing fields. And as you saw on that graph, even to take off 50% of the training data, you're still at probably, maybe only 60% population. So you're putting a lot of bias and a lot of error into the model to begin with, right? How you do expect it to actually do a good job after that. So that was problem one.
Yeah, and I guess this passes through throughout the entire timeline of the project, because it weighs on what we're going to be doing with our model selection. It weighs in on every element. So one of the things we encountered was that we had a lot of categorical data. So computers really like numbers, as it turns out, but categorical data, there needs to be some method of encoding that, which I'll get to. But I guess with this, an example would be the name of someone pertinent to the case. If they were prevalent, if it was an expert and they were prevalent in 100 or 200 different cases, that name may have been written out 12 different ways, and it really seemed as though that was explored to the furthest degree. So we built a lot of our own custom tooling around that, and it's not necessarily that simple of a problem. So if there was a doctor involved on the case, these are just a small subsample of what we might have encountered around that. So the techniques around that was a lot of regex, the Levenstein distance, which is basically just a metric of how many letters in the word have changed, it assigns a value to that, was another way to kind of fuzzy match that information. And then there was also the need for human intervention, because there were cases where it was ambiguous, such as the second from the bottom. And then in the bottom case, there's really not a lot we can do with that, especially with such a common name as an example. So on to imputation, filling the gaps. So I did up this little image, I guess, two fundamentally different, two delicious cheeses, but fundamentally different in structure. And I guess what we need to do is somehow fill in those gaps and weigh up the balance between exploration and exploitation within the data. So the two methods that we kind of went with, one of the most common in the data science community is to just use a mean imputation. So that is for each feature within the data set, you would get an average over the rows that are actually populated within the data set and replace the unpopulated values with that. One of the most common mistakes as an amateur data scientist would, as Nick said, be to fill not a number and kind of substantiate that as 0 or none. But if the range of the values is between 100,000 and 200,000, you're fundamentally distorting that data by introducing 0. So a mean is a way of kind of flying under the radar to a machine learning model because it essentially is smack bang in the middle of what the model might expect to see for that feature. So it's basically not going to do a whole lot with it. But a more sophisticated method was using regression. So this is actually taking the data that was available and learning on that. And certain decision tree models, we'll get into models, but certain decision tree models are actually able to work around the holes in the proverbial cheese. So, I guess it was about, again, learning from the existing data and actually taking the desired learning goal, and this is supervised learning, and then back propagating it and filling in the gaps there. So that brings us to encoding. So as I said, a lot of these features were categorical. And I guess what I'm getting at with this diagram is that, as I said, computers kind of need to look at all of the data as some kind of numeric value. And given that it's a lot of, like, all of the analysis is reliant on manipulating numbers, you can't just assign a categorical feature to a basic numerical encoding. You've really got to think about how you're going to assign a number to that. So if you were to say that we'll just take them in order. So we've got apples, oranges, and pineapples. Give apples number 1, encode oranges as 2. Sure, encode pineapple as 3, and it stacks up, but it doesn't make any sense. And so that's, I guess, that's the most rudimentary method. It does work in the cases where there is some ordinality within the features. So the example here was the education level. You could potentially assign a increasing number for education level. And so any statistical measures that are made within the learning systems can potentially make some sense of that, but also how can you really say that 2 times high school equals undergrad, or undergrad plus high school equals postgrad? There's assumption there. So, a way of avoiding this bias is actually to use one-hot encoding, which is to break out. So if you've got a feature, so take the example of education level. If you've got a feature and there's 3 unique categories there, you might break that out to a feature for every category, and you basically just give a binary representation of whether that applies in the particular example or not. The powerful thing, especially in the legal case, was that in a lot of our examples, for a given case, say it was a medical professional working within the case, there might have been 6 medical professionals. And so the great thing about this is if there's 6 distinct medical professionals within the medical professionals category out of, maybe a few hundred or 1,000 that could potentially be selected. You can set any of those values in that row as 1 or 0. So it was a pretty quick and easy method of encoding multiple values that basically sit within a single cell. Now, it is unfortunately a very sparse representation, and there's a limitation on which kind of models will work well with this kind of data. So something that we found to be very interesting was impact encoding, or it's also known as likelihood encoding in the data science community. So there's a basic kind of pseudocode around that, but I guess basically the idea is this is another statistical measure that looks at the outcome. So within the training set, it's supervised learning, so you would have a desired goal that you're training to meet, and then checking that against a blind test set. But at least within this training set, we can take that information and feed it back into how we might be encoding our categorical features. And so to maintain kind of uniformity across the data set, you do something called bucketizing, which is, in layman terms, it's just splitting the data across buckets. And finding the mean value for any given unique feature within a category. So again, if we had 200 doctors that had worked on, all of these, every case ever, there's 200 unique doctors across that, we might bucketize the data into 5 or 10 buckets, and then within those, look at the tally of, okay, well, Dr. John Smith in this bucket, this was the average outcome of the case for those that he worked on. And then you kind of take a mean of means, you sum all of that up, and what you get is kind of a best approximation of that unique category's contribution or impact within the case. So, this is kind of leading into the actual model architectures and learning, and that's the method of normalization. So often you can improve the accuracy within models if you normalize the data. So that would basically, if you, once you've done all this numerical encoding and you've got a huge array of numbers, you want to standardize the variance and mean within each feature. So you're shifting the data around and you're scaling it in a way that certain models can have a much better chance of understanding it. It standardizes the information for them. You don't actually lose any information in this process. All you're doing is kind of changing the size of the frame. So that's most beneficial within DNNs and linear models as well. Tree models, which we've actually had a lot of success with, don't encounter this so much, but it made sense to try this, and it's definitely, there's been nothing lost from this, so it's a common procedure and it's worth doing. So that kind of brings us to the learning. So as I covered, after this entire process, we were left with a scarily small amount of nice data, very nice data, and it was a glory to behold once we'd done all of this. But especially after one-hot encoding, there were cases where we had more features than we did examples, and that's a pretty challenging supposition. So again, we had to be pretty tactical about how we were going to explore this feature space. So what we needed were models that were focused enough to find the strongest possible approaches, but Sorry, yeah, so this is the exploration versus exploitation problem, which is, it's a general artificial intelligence problem. It's seen across reinforcement learning as well, and some of the things that are really pushing the cutting edge at the moment. And so it's not going away. And so, yeah, so we needed to be able to explore this very broad feature space and then focus on those strongest approaches once they were found. So we landed on H2O. Previously in my work, I'd done a lot of stuff with TensorFlow and PyTorch. But H2O is very powerful and designed as a product for enterprise. Have productized a lot of their research, but they've also been great in that they've shared a lot of their open source libraries and provided some really excellent implementations of some powerful machine learning architectures. So they're deep neural networks, random forests, generalized linear models, gradient boosted trees, and then ensembling techniques as well. And then we were pretty overjoyed to discover that they'd open sourced their implementation of AutoML. So that's automatic machine learning and automatically searching through the hyperparameter space. And that was, the first keynote was kind of December last year, and it's, I think by around April the library was pretty hot. So, what automatic machine learning basically does is all of these architectures that I just listed, it will explore via a grid search over those. It is quite parallelizable. They have been, we inquired about this, they've been a bit reluctant to release the GPU version. So we had a bit of work in the background there, figuring all that out. But so it's basically performing a grid search, an exhaustive search across model architectures and hyperparameters. So these are the parameters that aren't necessarily at all related to the data. It's all of the kind of knobs and switches that are attached to the architecture. Now, this is currently running on a box somewhere right now. So we're still working through these results. Like, this has been running for over a week. So it's brute force, but it's very accessible, and it does a lot of that legwork and a lot of that exploration that we were concerned about. And then once it finds the jackpot, that's where the exploitation comes in. But kind of in parallel, we were working with XGBoost, which is a specific implementation of gradient boosted trees, the extreme version. So there was a paper, there's the name of the paper there, and there's been an open source library developed around that, and it has done extremely well on these kinds of problems, and is highly regarded within the Kaggle communities, and it's been one of the best performing, often within ensembles. But this is essentially an ensemble model, so it's running, it's trying a heap of things in parallel, which is a tree search. Connor, who's working on our team, had the brilliant idea of combining XGBoost with an evolutionary algorithm or a genetic algorithm. And what I said with AutoML about the grid search was that it's exhaustive, but it's brute force. And the powerful thing about evolutionary algorithms is that they'll search the feature space much more elegantly. So we wrote our own customized evolutionary algorithm around that. And for every time we ran XGBoost, we'd get performance metrics back. And so this was the kind of methods that we use. So we take, for every generation, we'll take the best performing 25% of those models. We'll add some noise or some randomly generated new models. And then for the other half, we will allow intermingling between the best features and, the best models and the remainder of that gene pool. And we were seeing it would converge pretty rapidly within 7 to 10 generations. As Connor aptly pointed out, like, you could, just the same as our evolution is boundless, we could be running this for much longer, and that'll probably be further research. But this pretty quickly was found to be favourable. So, as I've said, they're much more efficient than the grid search, and it's a much more intelligent exploration via artificial natural selection. So, and then just a little
Little plug.
Little plug for our new research team. So, we're pretty excited to be able to work at the kind of intersection between industry and academia, and I think Max Kelsen as a SME is able to be, reading a paper the day it comes out, and the next day, like, hacking it and just pushing at the edge of these things. And then we've got, at the same time, pushing products. So I think we sit at a really interesting point there. Nick's been, like, really encouraging around building up our research capacity. So it's currently looking at the OpenAI retro contest. So that's a reinforcement learning algorithm that'll play Sonic, and it already looks like it's doing a lot better than a human. But so that's been supported a lot by our collaborations with IBM. They've provided us some really, really cool hardware that we're playing with on that. And of course, there's our genomics collaborations as well with QIMR and Genomica, doing some really interesting applied ML in the space of cancer diagnoses. So I'll pass back to Nick to...
Thank you. I did warn you he was going to get technical, right? I forewarned. I think what's interesting about Athon's talk for me, before I pass back to Sam to do the legal bit and the main spiel, is that I think what we came up against in this project was a bunch of techniques and even frameworks that you don't normally hear about at events like this. A lot of the conversations tend to be around Tensor and PyTorch, like Athon mentioned. But this really pushed where we were at, and we were forced to kind of look again at what was on the market and really take a first principles approach to getting the best outcome, and try a lot of different approaches, right? Work through a range of different things. This wasn't something that was immediately obvious or a solved problem. And that's kind of where we're at with research, which Athon introduced. We're super excited to get stuck into some problems right on the edge, which can feed back into our team that's working with our clients to deliver super cool solutions. So I'll hand it back to Sam.
Yeah, and I can concur to that, because when we started out, we started talking about some common kind of platforms that even I was aware of. But then each week when we would meet and we would talk about some of the challenges that we'd come across and how we're overcoming them, we'd be talking about a different model and a different method. And so I'd get a new paper sent to me, which I'd then try to read and understand what we're actually doing and how we're actually using that. And so it was evident that there was a lot of complexity in what we were trying to do, and overcoming the data sparsity issues was up there with some of the bigger challenges that we have. But I think while we are, like, in the last couple of days now of running the model, we had hoped to have finished by now, so that we were talking through where we've actually landed. But we're still going to run the model for a few more days. But even so, I think where we have landed now is in quite a good position, given that we've really only been in the detail of this for what are we now? We're just 4 months now, I think, that we've been going. So the outcomes. The natural language understanding, so all our data extraction, our classification, taking all of that unstructured data and turning that into a structured data that fed into our model, we were able to, and I think we had around about 30, just over 30 features that we were able to derive from these documents. And we had an accuracy rate of 82%. So that was, like I found it a very successful program and a very successful, solution to a problem that initially seemed potentially insurmountable. So we've now got this, that we can now continue to use the natural language element of our model for other applications, for continuing to develop the model. And now Nick and I are going to talk through the model outcome. And so as I said, like we're still running, this is still running right now as an Athon. Yeah, so I think it's due to finish on Monday, or is it just on auto, and it's auto ML, and it's just going to continue until it feels that it's finished? Yeah, okay, we'll put a stop at some point, great. So the mean absolute percentage error that we've had for this, so for these indicators that I was talking about earlier, these indicators that we're trying to derive from our model that would then inform us early on around those particular indicators. And I am being deliberately vague, sorry. Like we're at this point where it's still quite commercially sensitive, so I can't go into a huge amount of detail, but we're trying to share as much as we can. So, and I'm not a lawyer, so you can understand that I would be being vague if I was a lawyer, but I'm not, and I'm still being vague. So where we've landed is, for these indicators, we have a range of about 11.6 to 32.5%. Of mean absolute percentage error. And so this to some means a lot, to others it might not mean a great deal, but I guess if you look at that compared to what we then compared this to what humans had predicted, and we ended up with a performance improvement over what the humans predicted, at a rate of 23 to 48%. And so while some of these features that contribute to the outcome are at different stages in the life cycle, they're still very early on in the life cycle, so they're not they're not identical to when the human predicted, but they're very close to when the human predicted. And even though we're still running the model and we've still got the last few days of it to run, but even so, we're already showing a marked improvement over what we can predict, what humans can predict in these particular cases. And so I think that's it's quite a substantial and a notable achievement that we've been able to get from this.
I love beating humans.
Well, you did it.
We'll know more on next Monday.
Monday, Athon? Yeah, excellent. It's been Monday for about a month now, but Athon never stipulated which Monday, which is to be, he did say next Monday, just not which one. Looking at the opportunities for AI, I mean, there's a lot of talk of AI and how it's going to disrupt industries and how it's going to, make a considerable number of jobs obsolete in the future. And so we've been really looking at this, and there's right now there's a number of applications that AI can be applied in the legal industry, and be it from the prediction work that we're currently doing now, to natural language classification aided discovery, to conversational intelligence with chatbots. Like there's a number of areas that right now the capabilities exist and the applications for that and the opportunities to exploit that exist right now. But is this really the future? Like is this a game changer? Or is it us just, is it just staying relevant? Because all of these things, they're just augmenting what we're currently doing now. And they don't actually, on their own, they're not actually changing how we deliver legal services. And so we believe that the focus needs to be on radical change to business models, which we see, the convergence of AI and other exponential technologies as being a huge element of that. And so, and we understand that, in our backgrounds in the matter of, ERP and business systems projects and other areas of large structural change that we've gone through over the years, is that incremental change in organisation already faces enough internal resistance, and that trying to deliver any kind of disruptive change from within will ultimately be suffocated. And so NERV was formed with this in mind, in that if we are going to drive real disruptive change, to try and do that from within the organisation is not going to be effective. It will fail. You will not get off the ground because the organisation acts like an immune system. When you when you propose a fundamental change to its business model, its operating model, the structure, the culture, the values of that organisation, the immune system will win out. It will try to bring you down. And so NERV was formed instead of staying within the existing legal businesses. It was spun out to be an autonomous entity in its own right and to operate outside of the other legal businesses. And for this very reason, to look at how do we look at fundamentally different business models. How do we look at leveraging AI and other exponential technologies to help us craft a new business model that challenges the economics of the current legal industry. And it's with these technologies, it's with AI. It's when you start actually working in it that you then start to see the real capabilities and the real applications that it presents. Because like I look at where we were 6 months or 9 months or 12 months ago, and the ideas that we have now are vastly different to the ideas that we had in the past. And the reason for that is that when we started down this journey and we start to see the power of these tools, and it starts to give you these ideas that you didn't, it shows you where you can apply this and how you can solve problems that were previously, fulfilled with bums on seats and existing traditional business models. And it gives rise and gives opportunity for new business models and new platforms potentially to be created that will provide compelling value propositions that will challenge the status quo. And so we felt that being in and just doing something, like even though we know this is a huge piece of work, and it gives you a capability that has enormous potential, but that on its own is not going to change the industry. It's not going to offer a new proposition. It's one component of it, but just doing something is better than is the first starting point, and doing something and being clear that this is just contribute to an incremental change and not to a revolutionary, more disruptive change. Being clear about that, but then still progressing and still chasing that disruptive model is critical. And so I guess that's what we want to do. This is one part of it, of the puzzle, and it's only the start. And we're in Brisbane, so and AI is such a growing industry in Brisbane. We say, why not revolutionise the legal industry in Brisbane? So, yeah, why not?
Thanks, Sam. And I mean, I just want to extend a thank you for taking us on this journey. It's been a huge amount of fun. I guess tonight we've talked, you know, a little bit technical, but a little bit about how to execute a big, complicated AI project and how to work through problems that come up when you're actually putting one of these things into practice. And that's super interesting in itself, right? We're going to see more and more of this. The further that artificial intelligence creeps into industry, the harder these problems get, not necessarily because they're hard problems, but because the circumstances within which they're trying to be executed are hard. And as you made the good point before, change management and taking people along with us on these journeys is really, really, really important. So we definitely see Nerve as a partner of ours, and we're really excited to see where we go over the next couple of years. So thank you.
Thank you. Thank you everyone for coming and listening to us talk tonight, and I hope everyone was able to take something away.
All right, thank you very much, Sam, Nick, and Athon. Before we all leave or continue networking, is there anyone with questions? We'll go around and we'll take as many as possible.
Sam, question to you if I could. Really very interesting, but I'm wondering if you could reinterpret that for me in pragmatic, commercial and monetised terms.
Which bit? So what we're talking about with generating or creating a new business model. So I don't know if I'm going to be able to answer that in the time that we've got, but what I'm saying is we see AI, well not just AI, but any emerging technologies as being a fundamental building block to enable a different business model that is not solely reliant on resources, human and capital resources, in order to construct that model and provide services as part of that business model to create and capture value. We see AI as and other emerging technologies as that platform that allows you to create a scalable organization which is lower cost, that's significantly lower cost, to the point that your marginal cost of supply should be approaching zero. If you're able to acquire new business without having to put, for every $1 of revenue that you're able to generate, you're not having to cough up 70 cents of fixed cost and variable cost in order to be able to generate that. We see AI as being a critical part of that, and other industries have been doing that, but legal is not doing that. And we're not saying that we do away with humans by any means. Like, humans will still play a critical role in it, but we're just saying that it provides that platform, the tool to be able to underpin that, I guess.
I've seen a case study which translates 300 billable hours to 15 minutes using AI to create a substantial contract management document. Are we talking those terms?
I think you need to look at your pricing mechanism and how you go to market. Like, you can't, I know what you're saying. Traditionally, that a lot of legal services are based on billable hours. Now, if you reduce your billable hours, you reduce your revenue. So that's why we're saying it has to be an alternative business model. It can't be the same business model augmented with technology, because what are you doing? You're reducing your capacity to bill. You have to look at what is a completely different model of providing legal services, where you're still obviously generating revenue, but you're not dependent on bums on seats and billable hours. And do I have the answer to that? I don't. If I did, I wouldn't be here. I'd be retired. But it's something that we are working to, and we have to have that in mind when we're looking at the problems, and when we're working with these technologies, because you've got to just be clear that you divide the line, that you are not, are you improving something, or are you making something new? And then when you're making something new, that's when you come up with alternative revenue generation models and alternative business models as to how you can generate revenue through alternative means.
For me, a question really with regards to the methodology. With so much sparse data, was there any correlation done between the type of case and the information features recorded per case? As in, my thinking being at a divorce case, the legal practitioner would record perhaps different information relevant to what they think relevant to the case, as opposed to a litigation side of things, and therefore an inference of perhaps a cluster of cases leading to bespoke models across the spectrum, as opposed to one size fits all.
We started actually with a very narrow domain, so we picked a very specific section of cases and a jurisdiction that we understood and that we had a good sample case for. So given that we were starting with a proof of concept and understanding whether this was possible, our first thing was to choose something to reduce complexity. So that would be an interesting analysis to run at stage 2, Sam. What we did do though is we did look at the effectiveness of different lawyers and the effectiveness of different branches and over time with their ability to record data. And we did find substantial differences between some of the locations, and particularly over time there might have been an organisational push to record data correctly and then it would drop back off and so on. So there's certainly a lot of factors at play with recording data. Competence and culture and time all being part of it. But it would be interesting then when we go the next step to take that to different fields.
We did actually find correlation between how complete the information on a given case was and the actual outcomes. So, yeah, quite interesting.
There's been a lot of work on formalist versus realist approaches and how judicial decision making is made. Basically, whether judges apply facts like a mathematical equation, or whether there's a more purposive approach where you cut facts together. You've got 30 categories that tell you what the result's going to be. Does that give you any insight on which way it is? Whether the facts actually matter or whether it's a more general purposive type idea?
It's a big question. Do you have thoughts on this? I have some thoughts. I mean, I guess from my experience of reading cases, a very unfortunate 6 years of my life that I'll never get back, it certainly depends on the case, right? So again, to go to the point, that we were dealing with something that was quite small, and we're talking about very fact-specific determinations. It's not a High Court judgment or a Supreme Court judgment that there's particularly some error, question of law at play, that we've got split judicial decisions. We're dealing really with quite fact-based information. Whether that scales, I have no idea. I'm super excited to find out. But I think where we started, there without a doubt is a correlation between the facts that we can get out of the supporting documentation and the variables that we were looking to optimise for.
And just to clarify as well, we ended up with 30 out of 30 features, but out of the natural language processing side. But then I think we ended up totaling about 88 features in total. So yeah, so it wasn't just those 30. It was 88 in total out of the 200. But yeah, hopefully Nick answered that adequately for you. Wonderful.
I have a technical question. You used to encode the categorical variables. Why didn't you use an embedding? Why did you use a random number and sample from it and take the mean, as opposed to an embedding of the categorical variables?
We did actually try feature embedding. That was a side experiment, and it was purely based on metrics. We weren't getting the performance out of it. So, we'd probably have to explore that in further depth.
Okay.
Anyone else with a question? Right.
If you've got this data, how do you know it's good? And who else tests for validity that your data and your outcomes are reasonable? Because if this is used for judicial as being expert witness, because of the data, how do you prove that your data is clean and untainted?
It's actually a problem that probably is not as relevant in this case, but is extremely relevant to a lot of what we're doing across ML and AI more generally. There's a paper that was released late last year about bias within image classification APIs. So the major APIs at Microsoft's, IBM Watson, Google Cloud, so on and so forth. A researcher had the clever idea of looking for error rates on passing different photos through the systems, and they found that the systems performed at about 2 to 3% error on white males, and then it performed at about 8% error on white females, and then it fell to 15% for males of colour, and then it fell to 35% for females of colour, right? No one sat there and said, we're going to make a shitty classifier for females of colour. No one thought that. But it was a bias that existed in the data set that was used to train those systems. And it just became inherent in the models. So it was actually quite a big paper, right? Because a lot of people are going, well, this is the simplest thing we do. This is the stupidest, dumbest example that we put out there that we go, we can tell you how old you are by looking at your face. But we can't do that well if you're not white and male and look like you're from Silicon Valley. So there's a lot of work that's gone into this. IBM have released a paper only about 2 or 3 weeks ago where they've got a pre-processing suite for detecting bias in data sets on the way in. Because one question is, well, you know, for say a prediction algorithm is, well, why don't you just remove gender, right? If we're worried about gender's effect, but the problem is that gender can exist across the data set, not just in a specific variable. So can age, so can race, etc. So we can't de-bias the data just by removing a particular feature. Moreover, that feature might be pertinent to the decision we're making, and we might be removing something that's really, really important, right? So that doesn't work. So you've got to work out a way of detecting inherent biases and hedging against them. And it's twofold. It's one, working with pre-processing and understanding the data you're working with and challenging it. But two, it's setting up robust testing regimes to ensure that those biases don't exist. The fact that no one thought to test females of colour across 5 major tech companies in public services is outrageous. And if we start putting that into banks to make credit decisions, or if we start putting it into the judicial system, we're going to be in trouble. I think the good thing is that the industry's woken up to this. There's a lot of dialogue out there about this. One of the APRA board members was talking about this just the other day to the banks. There's a lot in the GDPR regulation in Europe that's coming in that's causing the industry to really be a little bit introspective for once. We've moved so fast, the old Silicon Valley mantra of move fast and break shit. Now that we're actually affecting people's rights and people's lives, we've got to slow down and make sure that we don't break people's lives like Facebook broke society. So it's a really interesting space. There's a lot of movement. The other side of it's explainability. If I make a credit decision or if I make a judicial decision in a deep neural network, how do I explain how that decision was made? Moreover, if it's a privacy secure situation and I'm looking at the evidence that the network drew upon, how can I give that evidence? How can I expose it? These aren't easy questions, but they're very, very important. The federal government just last night in the budget announced that it's going to put $10 million into an ethics board at the federal level for AI in Australia, which I think is a really, really positive move and it's the right thing to do. So we're going to see a lot of movement, but it's a great question.
Hello, yeah. I've got kind of 2 questions. The first one is the cases you looked at, the 15,000 cases, were they civil or criminal cases?
They were civil.
Civil, yeah, okay. So if you analysed them and came up with a solution or a figure that says you're getting better than... were they cases that were finalised?
That's where we went from 15,000 down to the 10.5 for 10,800 for finalised cases because we needed to have outcomes in order to train the model.
Right. So if you got then a model that told you were getting a 23% better than humans, if the case was finalised, how did you get a better result?
Because of the estimations that were provided by the lawyers at the point in time. So all the cases had estimations for particular indicators at the outset of the case. And so that's what we then created, so that we had something that we could measure it back against, as opposed to, what do we get, like getting someone now to do a prediction, a human to predict the outcome of the case that settled, 5 years ago, once they already had the information. So we had that captured early on.
Right, so part of the features were you had the estimation, then you had the results, so you could compare them.
Okay. That's right.
Yeah.
Any other questions? Yes.
All right. Just some technical questions. With something like backprop, you're talking about for missing values, you're taking the mean for basically missing values. Why didn't you just use the prediction of the network as the output for missing values, so it wasn't actually backpropagating an error in those cases?
I think when I don't know if this is on, but I think when I referred to the backpropagation, that was actually the process you're talking about.
Okay.
So I use backpropagation as in the terminology of the way that works.
But did you use the output of the network
Within the training set, yes.
for the hidden values?
Oh, right.
For the missing values, sorry.
That's actually something, now that we're finalising our results, that's something that we're going to be doing. So we'll be pulling those results back in through imputation and growing it from there. So,
And the second question is about using a GA, genetic algorithm. For so I guess what you're trying to do is you're searching the parameter space using a genetic algorithm, but a genetic algorithm itself has parameters that you have to fine tune. So what is it that's preventing you from falling in a local minima using a genetic algorithm?
good call. So we did a lot of reading up on genetic algorithms, and we did set our hyperparameters, and we explored that space to the best degree that we could. It was more, we saw it as a quick way to explore that space. Yes, the genetic algorithm has its own hyperparameters, but it was the proof was kind of in the pudding in comparing it to more automated or more brute force methods. So we found it to be more elegant, and it landed on better, just empirically better results. So
Cool. Thank you.
Anyone else?
So just to take up on that genetic algorithm, you mentioned in the slide randomisation. I presume you mean mutation, so you just tweaked a couple of elements with regards to that 50 or 25%, whatever you did?
yeah, there was 25% was randomly selected from the complete feature space, and then this one works. And then there was also mutation within the breeding, within that 50%. So there, we added, I think it was maybe 5% randomization around that as well, in terms of the hyperparameters.
Hi, this is regarding the missing data imputation that you did. The question is, like you can only impute the missing data when it's missing by at random or missing completely at random. And this is one of the biggest challenge I have. Like whenever I get a data set, I don't know whether it's missing at random or it's missing purposefully. Like how did you identify that? It's based on your knowledge on the data, or did you have some kind of a smarts to identify how it's missing, whether it's not done deliberately?
So manually. So what we did with the help of someone in the crowd is we went through all of these features to determine what should have been captured, or what, and so it was omissed as an error. So the lawyer should have captured it, but they didn't. Or if it's not a mandatory input, as in they didn't have to provide a response to that particular case. A response is zero. So, for instance, what could one of those be, without going into too much detail? There's just particular instances where the answer is zero, and it was about making that determination of where they should have captured it but they didn't, or where an actual answer was zero. But that was manual, not to the 15,000, just to the 200 features.
Hi, hello. I have a similar question about missing data. So you mentioned that one of the issues and the challenge with the project was that not all of the data were available. And my question is, if there would be better quality of the data, do you think that prediction model could be even better, that you'd have higher and better difference than 20% compared to the professional judgment of the lawyer when they are estimating the case? Or did you compare this if you do evaluation on smaller group of data with the complete data set?
So if I understand you correctly, when we compared the accuracy of the model against what the lawyers had predicted, it was on the same the same sample of data that was fed into the model. Athon, you can confirm that for me though.
The question was about whether we think A, the predictions would improve if we had a complete frame of data, and B, so to answer the second part first, we just didn't have enough data to run that analysis, right? If you looked at that graph, basically the fourth feature was not fully filled. So we didn't have a data frame, basically period, that was fully filled. So we had to impute at some point. So we had to draw that cutoff where we felt it would be most efficient. We haven't done a lot of playing, to my knowledge, of where that sits. It's pretty...
all the way up to maybe 1,500 or 1,000. So yeah, there were some insights around that as well.
And the question, would it be better with a full data frame? Yes, absolutely.
Yeah, how much would be better? Do you estimate or difficult?
You couldn't speculate,
yeah,
really.
Yeah,
the time will tell.
Okay, thanks.
Question on application and commercials. When you reduce the number of hours that you spend, how does that affect your billing? Do you pass on the cost savings to the client? And if you do so, how do you actually maintain profitability?
Sorry, I thought it was going to be a technical question. Could you ask that again? Sorry. Sorry. Oh, it's a very good question. I think as I was saying before, if I had solved that now, I would be retired and not be here. But we see the only way of being able to do that is to change the, it has to be around how you charge for your services. And it can't be the same traditional method of being able to charge, hourly rates for the hours that you work. Because if we're looking at alternative business models, it's simply not scalable. And we think there are better ways of being able to deliver services, legal services, but not in the traditional sense. I don't know that's vague, but it's a problem that we are really trying to work through, and we don't have an answer yet. We have several hypotheses about how it potentially could be delivered, but it's a bigger and probably not a conversation that I can go into a lot of detail. But you're right, that has to be we have to overcome that, and I think it's the difference between, as I was saying before, augmenting how we currently deliver, because you're removing your ability to charge if you just augment and reduce the hours that it takes to build.
It becomes a problem, because I'm facing this problem right now, because by improving your methodology and you charge less and your competitors are charging more, you got to still maintain that perception in the market that people are paying for a bigger service than what they're getting. and managing that perception where when you pass on the cost to the customer, how do you manage the feeling that they're getting an inferior product, possibly a stemming out question, when your competitors are charging more and you're charging less?
Look, I think, yeah, what do you propose? No, I think like any industry that goes through a structural change where the economics and the cost structure of that industry change, and therefore the margins change, I think as soon as one starts to do it, the others are going to be forced to do it, because if not, you're then in a position where you're able to, for one, you could either maintain high margins and charge the same as everyone else, but at a very different cost structure. But as soon as you do that, then everyone will, leech onto that, and people will start undercutting you, and that will drive the price down. Just, yeah. Sorry, oh yeah, you're going to help me with this one?
This is disruption at the coalface. Some people will use AI to improve their results and take cases to court that wouldn't have otherwise gone there. As a result, people will flock to them. Those that have sold time without value are in real trouble, and so they should be.
Thank you.
All right, we'll have one last question, and then we can all continue doing that work and finish eating.
A really simple question. Can you literally define what you mean by features?
Oh, the variables.
Yeah.
So any think of like a regression model, all of your independent variables that make up your model to predict your dependent variable.
Okay.
Cool. Right. Very cool. Thank you all very
All right.
much.
Thank you, everyone. Thank you, Nick. Thank you, Athon.